Welcome to G Fun Facts Online. Today, we are going to dive deep into a substance that you likely interact with every single hour of your life, yet it remains one of the most baffling mysteries in the entire field of physics. We are talking about water, but not the water you drink or shower in. We are talking about deeply supercooled water, a state of matter that exists in a temperature range so unstable that scientists call it no man's land. For decades, this zone was a black box. We knew something strange happened there, something that might rewrite the textbooks on thermodynamics, but we could not see it because the water would freeze faster than our instruments could measure it. However, thanks to a golden age of discovery in the 2020s, using technology like atomic strobe lights and miles-long particle accelerators, we finally have an answer. It turns out that water is not just one liquid, it is two distinct liquids fighting for dominance. Today we are going to explore the observation of the liquid-liquid transition below freezing, how we finally saw it, and why this matters for everything from detecting dark matter to preserving human organs for transplant. To really understand the gravity of this discovery, we have to start by acknowledging that water is a chemical eccentric. It breaks almost every rule. Most liquids get denser as they get colder. They pack together tightly until they freeze. Water plays along until it hits 4 degrees Celsius. Then it goes rogue. As it cools from 4 degrees down to 0, it starts to expand and become less dense. Then, when it freezes, it expands violently. This is why ice floats, which is great for fish surviving the winter, but a nightmare for your pipes. But here is the thing. Water only freezes at 0 degrees Celsius if there are impurities present. We call these nucleation sites. Things like dust, bacteria, or rough surfaces give the ice crystals a place to start growing. If you take ultra-pure water and put it in a perfectly smooth container, with absolutely no vibrations, you can cool it well below 0, and it will remain a liquid. This is called the supercooled state. In the 1970s, researchers Austin Angel and Robin Speedy pushed this to the limit. They found that as you cool water down further, its anomalies go into overdrive. Its capacity to hold heat skyrockets. It becomes easier to compress. It acts like it is approaching a critical point, a mathematical singularity, where physical properties blow up to infinity. But there was a wall. Around minus 40 degrees Celsius, the water would inevitably flash freeze. It didn't matter how pure it was. Below minus 40, the liquid state seemed impossible to maintain for even a microsecond. This unobservable region, roughly between minus 40 degrees and minus 113 degrees Celsius, was dubbed no man's land. It is a zone where ice crystallization is so rapid that traditional instruments simply cannot measure the liquid's properties before it solidifies. For years, this was the end of the road. But in 1992, a team at Boston University, led by Peter Poole and Gene Stanley, proposed a radical explanation. They ran computer simulations and suggested that the critical point researchers were sensing was real, but it was not a transition between liquid and gas. It was a liquid-liquid critical point. Their hypothesis was stunning. They suggested that below freezing, water wants to separate into two different liquids. Imagine a vinaigrette salad dressing. You shake it up, and it looks like one liquid, but if you let it sit, it separates into oil and vinegar. The hypothesis was that supercooled water is trying to do the same thing. It wants to unmix itself into two distinct forms. The first form is the low-density liquid, or LDL. In this form, the water is structured and open. Every water molecule forms 4 strong hydrogen bonds in a shape called a tetrahedron. Think of a pyramid with a triangular base. It is essentially liquid ice. It has the geometry of ice, but it still flows. The second form is the high-density liquid, or HDL. This is a disordered, collapsed structure. The molecules are jammed closer together. The perfect pyramid shape is broken, and molecules squeeze into spaces they should not be in. In our daily life at room temperature, these two forms are indistinguishably mixed. They fluctuate back and forth nanosecond by nanosecond. But in the deep freeze of no man's land, the theory predicted they would separate. For nearly 30 years, this remained a controversial theory. It was supported by computer code, but unproven in the real world, because no one could take a picture inside no man's land fast enough. Proving the existence of two waters required observing the liquid inside that forbidden temperature zone before it could freeze. This is a race against time. At minus 100 degrees, water wants to become ice in microseconds. To see the liquid, you need a camera that is faster than the freezing process. This brings us to the 2020s and the entrance of the X-ray free electron laser, or XFEL. These are miles-long particle accelerators that generate X-ray pulses a billion times brighter than the sun. These pulses last only femtoseconds. That is quadrillionths of a second. It is effectively an atomic strobe light. In 2020, 2 landmark experiments used these machines to finally peer into the forbidden zone. The first experiment was a collaboration led by Stockholm University using the PAL-XFEL in South Korea. They used a clever backdoor to enter no man's land. They didn't start with liquid and cool it down. Instead, they started with high-pressure ice and melted it. They took a glassy form of water, created under immense pressure, and used an infrared laser to heat it instantly while simultaneously releasing the pressure. For a fleeting moment, the sample became liquid water at -70°C. Before the water could realize it was supposed to be ice, the team hit it with those femtosecond X-ray pulses. The X-rays scattered off the water molecules, creating diffraction patterns that revealed the atomic structure. The results were unambiguous. As the pressure dropped and the water expanded, the X-ray fingerprint shifted dramatically. It didn't change smoothly, it jumped. The liquid transformed from a high-density disordered structure to a low-density tetrahedral structure. The discontinuity was the smoking gun of a phase transition. They had caught water in the act of switching identities. Around the same time, a team at Pacific Northwest National Laboratory used a different approach. They created a microscopic film of ice on a platinum wafer in a vacuum. By heating the ice with a nanosecond laser, they melted it into a supercooled liquid for just a few nanoseconds before it refroze. Using infrared spectroscopy, they watched the water molecules dance. They observed that at extremely low temperatures, the water settled into a structure that was distinctively two-state. They could effectively see the signature of the low-density liquid winning the tug-of-war against the high-density liquid as the temperature dropped. Their conclusion was that water is indeed a mixture of two structural motifs. So what exactly is happening at the molecular level? To visualize it, we have to look at hydrogen bonds, the Velcro that holds water molecules together. In the low-density liquid, water behaves like a master architect. Each oxygen atom grabs two hydrogen atoms from its neighbors and offers its own two hydrogen atoms to others, forming that perfect tetrahedron. This creates an open, spacious 3D network with lots of empty space in the center of the cage-like structures. This openness is why ice is light. In the high-density liquid, that architecture collapses. The thermal energy, or high pressure, forces the molecules to jiggle out of their perfect alignment. The hydrogen bonds bend and distort. Crucially, a fifth water molecule often squeezes into the space that would be empty in the tetrahedral arrangement. This interstitial molecule increases the local density. The theory posits that if you could map water's behavior on a graph of pressure versus temperature, there's a line separating these two liquid phases. This line ends at a specific point, called the second critical point, estimated to be around -83°C and 1,000 atmospheres of pressure. Beyond this point, the two liquids become indistinguishable, but as you move away from it into no man's land, they separate. The fluctuations between these two states, near the critical point, are what cause water's famous anomalies. Why does water expand when cooled? Because as it cools, the equilibrium shifts toward the spacious low-density form. Why does compressibility increase? Because near the critical point, the fluctuations between dense and light forms make the liquid softer and more responsive to pressure. Now, science is rarely a straight path to truth. It is a series of arguments. Despite these breakthroughs, a faction of the scientific community remains unconvinced. This is the debate between the mixture model versus the continuum model. The mixture model, which argues for two liquids, has gained the upper hand recently. But the continuum model proponents argue that water does not need two distinct phases to be weird. They believe water is a single liquid that simply undergoes continuous structural changes. There is also a thermodynamic challenge. In 2022, researcher Fumio Hirata argued that the simulation results supporting the second critical point might violate the Gibbs phase rule, a fundamental theorem of thermodynamics. He suggests that what looks like a phase transition in computer models might be an artifact of finite size effects. Essentially, because the simulation box is small, it forces the water to behave in ways that bulk water in the real world wouldn't. Furthermore, some skeptics argue that the XFEL experiments might be observing rapid crystallization rather than a liquid transition. Since the low-density liquid structure is very similar to ice, distinguishing tiny ice crystals from low-density liquid is incredibly difficult. The research teams argue their diffraction data clearly shows liquid-like disorder, not crystalline peaks, but the interpretation of data at the femtosecond limit is always a subject of intense peer review. While physicists argue over phase diagrams, engineers and biologists are already putting supercooled water to work. The ability to manipulate water in this state has implications that sound like science fiction. Let's look at three major applications. First, hunting for dark matter. Matthew Shadagis at the University at Albany has turned supercooled water into a subatomic particle detector. His invention is called the snowball chamber. It relies on the fact that supercooled water is metastable. It is desperate for an excuse to freeze. In his lab, water is cooled to -20 degrees. It sits there, liquid and calm. But if a neutron strikes a water molecule, the collision deposits energy that triggers a nucleation event. The water instantly flash freezes, turning into a snowball. The heat released and the camera footage of the sudden white crystal provide the signal. Shadagis proposes that this could be the ultimate dark matter detector. The leading candidates for dark matter are weakly interacting massive particles, or WIMPs. They interact very weakly with normal matter. But a collision with a hydrogen nucleus in supercooled water might be just enough to trigger that phase change. Because water is rich in hydrogen, which has a low atomic mass, it is particularly sensitive to low-mass dark matter particles that other heavy metal detectors like xenon might miss. The second application is biological time travel, or specifically, organ preservation. Perhaps the most immediate impact of supercooled water research is in medicine. Currently, a donor heart or liver can only be kept on ice for a few hours, usually 4 to 12. This logistical nightmare leads to thousands of wasted organs every year. Freezing organs destroys them because ice crystals act like microscopic daggers, puncturing cell membranes. But supercooling offers a third way: keeping the organ sub-zero without freezing. Teams at UC Berkeley and Harvard have pioneered isochoric, or constant volume, preservation. They place an organ in a rigid, sealed steel chamber filled with a preservation fluid. As the chamber is cooled, the water wants to freeze. But water expands when it freezes. In a rigid box of constant volume, it has no room to expand. The laws of thermodynamics kick in, and the pressure inside the box skyrockets, sometimes up to hundreds of atmospheres. This high pressure depresses the freezing point. The water remains liquid, even at -5 or -10 degrees Celsius. The result is that the organ's metabolism is suppressed much more effectively than at 0 degrees, extending preservation time from hours to days. In experiments, rat and pig livers have been supercooled for 3 to 4 days, and then successfully transplanted. If this scales to humans, it would create a global organ bank, allowing perfect immunological matching and saving countless lives. Finally, there is the climate. High in the atmosphere, clouds are often made of supercooled water droplets, not ice. These droplets can exist at -30 degrees Celsius. The ratio of supercooled water to ice in clouds is a critical variable in climate models. Supercooled water clouds reflect sunlight, cooling the Earth. Ice clouds trap heat, warming the Earth. Understanding the specific conditions under which the two-liquid transition triggers freezing helps meteorologists predict when a cloud will glaciate. This improves the accuracy of climate change forecasts, as the phase of clouds is one of the largest uncertainties in current models. The study of deeply supercooled water is a testament to the fact that the frontier of science isn't always on Mars or inside a black hole. Sometimes it is in a glass of water. The observation of the liquid-liquid transition is a triumph of modern experimental physics. It vindicates the 30-year-old hypothesis that water is a chameleon liquid, shape-shifting between dense and open structures to navigate the thermal landscape. This duality is likely the secret sauce that makes water the solvent of life. Its ability to fluctuate allows it to fold proteins, dissolve nutrients, and buffer thermal changes with unparalleled efficiency. As we peer deeper into no man's land, we are finding that the void is not empty. It is filled with a bizarre, two-faced fluid that holds the secrets of our universe, from the microscopic machinery of life to the invisible matter that binds the galaxies. The next time you drink a glass of ice water, remember, you are swallowing a mystery that science is just beginning to digest. Thanks for joining us on G Fun Facts Online.